Let's go for the next molecule, that is minus Pentenomycine. It's an antibiotic. The structure is five-membered ring with one CH2OH and one alpha OH. It's a five-membered ring. Looks smaller, but it's very challenging molecule because it contains this hidden carbohydrate moiety. It's not so straight. The retro of this starts with, so the structure with the aldol condensation. I mean, it's a reverse aldol, of course. So one can imagine the aldol between the CH2OH, CHO and CH3. So if you treat with the base, this is going to generate a carbon ion, going to attack here, and we will get the OH here, and then eventually we can do the dehydration to give you the double bond in this structure. If we go for the synthesis, that time it will be more clear. This is the C double bond O, so one can think of having the CH2 here and a five-membered ring. And this can be prepared from a five-membered D-glucose, protected D-glucose, which we have seen the structure earlier also. So one can imagine it's a D-glucose with a C double bond O here at carbon number 3, and this is from a normal D-glucose, which is a 6-member. We'll go all the transitions step by step to have a more clear synthesis. So this is retrosynthesis of pentenomycin. Let's go for the main synthesis. So I start with the synthesis. So here we'll take the D-glucose and treat with the acetone in presence of H+. So this D-glucose, acetone in presence of H+, will always protect the molecule in a five-membered ring, not the six-membered ring. So we will get a five-membered ring protection with the acetone. Always remember, when you protect with the acetone and H+, it will be a five-membered ring protection. Then we'll treat this with the CrO3 PCC. It's oxidizing agent. Only now this OH is free. We have blocked all the other OH groups, and therefore this OH on oxidation will give the C double bond O, which is this structure. And now we'll treat this with the mild base and MENO2. So it's a mild base and the nitromethane. This is going to generate CH2 minus NO2, and this CH2 minus will attack on the carbonyl carbon. Can you imagine? This is going here and this will open up. So we will get the product, which after acidifying will give you the OH here and CH2NO2. CH2NO2. This on first treatment with alkaline KMNO4, second by treatment with NaBH4, and third by treatment with BnBr in presence of NaH. NaH is a sodium hydride, a strong base in DMF as solvent, which is 1:1. So let's look at the step by step what happens. So in the beginning we will get the CH2NO2 in presence of KMNO4 getting converted into COOH. So this will become COOH. NaBH4 is a reducing agent. This COOH which was formed here will become CHO, then CH2OH, again NaBH4, and then this CH2OH on treatment with BnBr, which is a protecting agent, will convert it into CH2OBN. So eventually we will get a structure which looks like OH, OBN, and this protecting agent. So overall this CH2NO2 has become CH2OBN. This we treat with the H3O. It's a deprotection. So we will get now the free OH group. We have worked on carbon number 1, 2 and 3. So third carbon we have worked on, and now we'll make these only the deprotection of the corner OH. Okay, so here we get the deprotection of these two groups, and when we have a diol we will treat this with the NaIO4 where the diol will break from here and this carbon will become CHO. So we will get the structure. These are the protected ones. This is, we have again the protected this OH, and this group becomes C double bond OH. So then this is reduced with the NaBH4. We'll get CH2OH there. The rest of the groups are as it is. So we'll get CH2OH. CH2OH is protected with the TSCl in presence of pyridine. So we will get OBN and of course the OTs. Then we carry out a transketalization in with the MeOH and the acetal or ketal of acetone. So here is the acetone where we have a double bond. We add methanol, so we will get this ketal formation in presence of the H plus. So this ketal, what it will do, it will break these bonds and a new protection is between these two OH. So it will actually first the H plus will go and bind here, and then we will get first the breaking of this bond, and then the ketone will come here. We will get eventually the structure like this. OBN. So this is of course the alpha and that was beta, and this becomes OME and this is OH. Now this can be alpha or beta. We want a beta isomer, so we isolate. We do the isolation, so we will get the beta isomer. Beta isomer means this OH group is up. So we will get a structure that looks like the same with the beta OMe. Fine. Now this is treated with tertiary butoxide, potassium, tertiary butoxide, which is being a base will take off this proton it will have a negative charge, and that negative charge will attack here, and this OH will go off. So you can think of this will form a negative charge carbon, this negative charge carbon will attack here, and this OH will go. Eventually we'll get a CH2, double bond with the CH2. So OMe, OBN, and we will get the CH2 at this place. This is then hydrolyzed in presence of H plus acid, where the pH is maintained, and we will get this bond breaking. This remains as it is. So we will get the CH2 OH. So really it requires a skill when you do such reactions. One must have a thorough knowledge of which chemistry to be used at what time. So we get a geminal diol. Geminal diols are very unstable. They lose a molecule of water and form a CHO group there. So we will get CH2 OH, OBN. Fine. Now this is treated with alumina at 100 degree to 180 degree centigrade at 30 mm Hg, where we will get actually the aldol. So we don't do aldol in this case with the acidic condition or the basic condition, because we want to still protect this group. If you use the acidic condition or the basic condition, it's going to break this bond. So here we have the, of course one can imagine this is going to be a, to give a tautomer, where the, this is enol system, double bond and the OH on the same carbon atom. You can think of H coming here and the CH3. So I'll write down the same structure like this, CH3 and the O. I have just exchanged the positions. So we get C double bond OH. This will be easy for me to imagine my next reaction. This structure change I have done to do the aldol. Think of aldol. So now when I do the aldol, this will give a negative charge. That negative charge will attack on this carbon. This will open up, and we will get a structure that is going to give me CH2 here and the OH here. Okay, let us write down. So CH2, CH and OH. OBN, and of course then you can think of loss of this H2O, and you will get a structure. We will be almost to the end of our synthesis. Some protection, deprotection things to be taken care of. Fine. And now we use the debenzolation with the acetic anhydride in presence of H2SO4 and acetic acid. The benzyl ether will get converted into the acetyl ether. So we will get OAC. We treat now the enzyme with the enzyme lipase, where we get the deacetylation, and in presence of acid, hydrolysis is in presence of acid. So we'll get a final product, that is Pentenomycine. So this is your minus Pentenomycine. That's a final product. So you have to always imagine the retro and the total synthesis, or in between the synthesis which can be formed. So this is the final total synthesis of Pentenomycine.